Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be talking about the topic of single variable linear inequalities. In the past, we've discussed single variable linear equations, where we have the same quantity on each side of an equal sign. Now we're going to look and see what happens when we relate unequal quantities together. In particular, we're going to talk about what a linear inequality is, and then we're going to discuss what compound linear inequalities are. First, let's go ahead and define linear inequalities. I'm going to define a linear inequality by first saying, let A and B be a part of the real numbers. Remember this symbol here. This symbol, it looks like a C with a tick mark in it. That means is a part of or is an element of. So if this symbol right here represents the real numbers, we are saying that A and B are a part of the real numbers, okay? So A and B are any number on the number line, okay? Just imagine that, any number on the number line. So let A and B both be real numbers. Come on, here we go. Then a linear inequality in one variable, that's important, we're only working with one variable at this time. A linear inequality in one variable is written in the form A times x plus b. Now this is the form of a linear equation in one variable, a times x plus b. You can think of it like mx plus b, okay? And we're going to say, instead of it being equal to 0, we are going to say that it is greater than 0, okay? So we have ax plus b, some number times x, plus some other constant is greater than 0. But we could also say that it's less than 0. We could also say that ax plus b is greater than or equal to 0. And we can say that ax plus b is less than or equal to 0. So if you're going to have a linear inequality in one variable, it needs to be written in one of these four forms, okay? Or I should say, you can manipulate it to get it into one of these four forms, okay? The big takeaway here is that you have one variable and you're using one of these inequality signs. That's the important idea. Now, understand that there is a difference between an inequality and an equation. There's a fundamental difference. An equation, we said, you can represent that as a balanced scale. So imagine that you had a scale and one quantity was on one side, something like 4, and another quantity was on the other side. We could say x. Okay? That means x and 4 are the same thing. They are equal to each other, so we would say we can figure out what x is because we know that these quantities are equal to each other. When you have an inequality, a linear inequality, it's a little different. Instead of having a balanced scale, you have an imbalanced scale. Okay? Now, if you think about it in terms of a scale, one thing is heavier than the other. Say this is x and this is 4. Now, they're not equal to each other. X is not 4. They're not the same thing. Instead, one is greater than the other. This side, if we're thinking in terms of a scale, is heavier than 4. So we would say x here has to be greater than 4. When you work with an inequality, you are now going to say, you lose certainty with your number, right? You don't know the exact number that x is. Instead, you're finding all possible numbers that x could be. So you're saying for this situation with the scale, what could this unknown quantity be if it's heavier than 4? Well, it could be 5, 6, 7, 8, 9, 10, etc. It could be 4.1, 4.2, 4.3. It could be anything bigger than 4. That's what's different now when working with inequalities. Now we're going to have to solve for all possible solutions. Let's talk about how we can actually do this solving, in particular how we can do the manipulation to work with these inequalities. Now before, when we were learning about solving equations, we had to learn about some properties for manipulating equations, in particular the additive and multiplicative properties of equality. Those said you could add whatever you want to both sides, you could subtract whatever you want to both sides, and you can multiply or divide whatever you want to both sides. Okay, as long as you do the same thing to both sides, you would preserve the equality. The one side is still equal to the other side. When it comes to inequalities, we want to preserve the inequality. We want to stick sometimes with the one side is heavier than the other side, and we want to keep that. So let's go ahead and try to define some properties here. We'll say if A is less than B, okay? Imagine you had A and B here. They could be numbers or expressions, whatever. And one is less than the other. Then, what happens if I added something like C to both sides? What would happen then? Would I preserve the inequality? Would I reverse the inequality? Would the left-hand side now become bigger than the right-hand side? Would I suddenly get an equation? Would they suddenly become equal? Well, think about this with an example. Pick two numbers, 3 and 4. Let's add something to each side. Add 1, or maybe go ahead and add 2, or 20, or 28, whatever. Every time you add something, right, you increase the number by that amount. But you're also increasing this higher number by the same amount. So here you would get, what's that, 31? And here you would get 32. This side is still greater than this side. You increase them by the same amount. So we have just preserved the inequality, okay? It's still a less than sign here, okay? The one side's still bigger than the other. What if we were to subtract? What if we were to subtract the same thing from each side? So let's say if A is less than B, then A minus C and B minus C, let's see how these are related. Let's say we subtracted 5 from each side. 3 minus 5 is negative 2. 4 minus 5 is negative 1. Well, negative 1 is still greater than negative 2. And again, we're seeing we preserve the inequality, okay? Yes, you subtracted from a quantity, but you subtracted the other quantity by the same amount. So it's not like one is suddenly less than the other, all right? You did the same thing to each side here. You added and subtracted the same things to each side. You preserve the inequality. Let's talk about multiplication now. Let's say A is less than B. Then A times C and B times C. Well, if I had 3 is less than 4 again, and I multiplied both sides by 2 or 3 or 4, whatever, you'll see that even, yes, I doubled this side, but when this side was bigger and I doubled it, it's still going to stay bigger. So when I multiply both sides of an inequality, I will preserve the inequality. Same thing with division. If I were to divide both sides of the inequality by the same thing, the inequality would stay. Well, the one side still remains bigger than the other, okay? So this is the multiplicative property of inequality. You can multiply whatever you want to both sides and divide whatever you want to both sides, and it preserves the inequality. However, there's one catch to this, okay? All of this is the exact same thing as what we did when we worked with equations. It's the same properties. It's the same work, okay? Instead of having an equal sign, we now have just these inequality signs. But here's the catch. The multiplicative property. You can multiply and divide whatever you want to both sides, and you remain with the same inequality sign. This only works if C is a positive number. If you multiply or divide both sides by a positive number, you remain with the same inequality sign. The trouble is when C is negative, when it's less than 0. If you have some inequality, we're going to say A is less than B, then A times C and B times C, where C is a negative number now, that reverses the inequality sign. The same with division. If you have some inequality, like here A is less than B, then if you divide both sides by something C, and that C again is negative, you again reverse the inequality, okay? This is called flipping the sign. If you add, subtract, multiply, divide, you always preserve the inequality, except when you multiply or divide by a negative. If you multiply or divide by a negative, you have to flip the sign, okay? The reason for that, it's actually fairly easy to see if you work with numbers. So for example, let's say 3 and 4. Okay, 3 is less than 4. What happens if I multiply both sides by a negative? Like let's say -1. I would get -3 and -4. Oh, wait a minute, -3 is greater than -4. There we can see an example of why we're inverting the sign, why we're changing the sign, right? Instead of it being less than, now it's a greater than. It's helpful to see this on a number line. So let me draw a quick little number line here. Let's say here's 0, here's 3, and here's 4. Here's -3, here's -4. The trouble is what we consider greater numbers. Really, the bigger the number is in positives, the farther away it is from 0. So obviously, 4 is greater than 3 because it's farther away from 0. However, when you're in the negative direction, when you're on the left-hand side here, the farther you are away from 0, the less of a number you are, okay? So that's why when we kind of invert these and we make them negatives, we suddenly change the idea of what it means to be greater than. If positive number, the farther away you are from 0, the bigger you are. But in negative numbers, the farther away from 0 you are, the smaller you are. That's kind of an explanation for why it is that when you multiply or divide by a negative, you flip the sign. I want you to write that down. If you multiply or divide by a negative, you flip the sign. I want you to keep it with you. I want you to write it on your worksheets, write it in your notes, on your exit tickets, on the test. Always keep remembering that, because this is one of those things that can very quickly change your answers to a problem if you don't flip the sign. It's something that students tend to forget to do. Oh my gosh, I think I probably forgot to do it once in class, where I neglected to flip a sign because I multiplied or divided by a negative. You need to have it written down. You need to reference it. You need to say it to yourself 101 times, okay? Because it's something you have to remember if you're going to go and solve these inequality problems. Now let's do some practice actually solving these. Now, keep in mind, we only have two properties for solving these. You can add and subtract whatever you want to both sides, and you can multiply or divide whatever you want to both sides. Just make sure you're aware of what happens to the sign here. So we start with a less than sign. This side, whatever number it is going to be smaller than this side. So let's try to get x by itself. Let's see if we can isolate the x variable. Well, to do that, I need to get rid of the -2 and the -4. So let's add 4 to both sides. That will cancel out here. We'll end up with -2x less than, because we preserved the inequality, 6. All right. Now, how would I get x by itself? Because it's being multiplied by -2. Well, why don't I do the reverse of that and divide by -2. So we divide by -2. I just have a 1x now. And I have a 6 divided by -2 is -3. Now, what happens to the inequality here? Keep in mind, I just divided by both sides by a negative number. That flips the inequality. That now says x is greater than -3. Okay? So we had to do a flip here. I'll put a little note. Flip the sign. Okay, so we have x is greater than -3. That's our solution. Or I should say, those are our solutions. Okay, we no longer have just one value. We now have infinitely many values. We have a collection of possibilities. Let's try to graph this and see what's going on here. I'm going to draw a little number line. And I'll put in, let's say this is 0. Let's say that's -3, okay? I'll say this side goes off to positive infinity. This side goes off to negative infinity. I'm not going to put in all the other numbers on the number line because what's the point, right? You can if you want, but I like very simple number lines. I know where 0 is, and I know where my number is. So let's try to graph what it means to be x is greater than -3. What I'm going to do is I'm going to do this in red. I'm going to go to -3, and I want to highlight all of the solutions that satisfy this inequality. Everything greater than -3. That means all these numbers to the right of -3 are solutions. They all satisfy the inequality. So you could pick something like 1. 1's greater than -3, or 2, or 3, or 4, or -1, or -2, or -1.5, etc. All of these numbers, if they're on the right of -3, on the number line, then it's going to be a solution for this. Now, here's the question. What about -3? Is this point itself a solution to the inequality? Well, one thing you should say is, well, let's try to plug it in, and you will see that -3 is greater than -3. No, that's not true. -3 is not greater than -3. They're the same thing. They're equal to each other. So we need to indicate that -3 here, because it looks like I highlighted it. It looks like I included it in all of these answers. We need to have a way of indicating that -3 is not a solution, okay? Everything to the right of it is, but -3 itself isn't. So there's a couple ways of doing this. In some textbooks, what they'll do is they draw an open circle on -3. They draw an open circle to indicate that it is not a solution, while a closed circle, right, a shaded in one, would indicate that it is a solution. So we could leave an open circle here, and this would mean everything above -3 is a solution. Our textbook uses what we use for interval notation, parentheses and brackets. So I'm going to put a parenthesis on -3. Maybe let me try to draw that a little better. I'm going to put a parenthesis right there. What this means is the same thing as the open circle. -3 is not a solution, but everything to the right of it is. That's the idea of the parenthesis. If we were to include -3, we would do a bracket. A bracket is the same thing as the closed dot or the shaded in dot, okay? The only reason we change this notation is because it helps us with interval notation. That's really the idea here. It mimics interval notation. So if we were going to say, what is this in interval notation? Let me put the parenthesis back here. We would say, well, the interval would be, we have a low bound and we have an upper bound. The lowest bound we have is -3. That's the lowest of all of these values. And what's the highest? Well, it keeps going up to infinity, so the upper bound is infinity. So all these solutions, nothing goes below -3, and it goes off to infinity. Now, and of course we have to separate this with a comma, now we need to state whether or not to include -3 and infinity. Well, we just said don't include -3 because it's not a solution here. So -3 is not a part of the solution set. Infinity, remember in interval notation, we said always put a parenthesis on infinity, never include it because it's not really a number, it's a concept, okay? So this would be our solution in interval notation, -3 to infinity. And we put a parenthesis around each one. So this tells me if I want a solution to this original inequality, I can pick any number between -3 and infinity. Just don't pick -3. You can pick anything in between them, but you can't pick -3. That won't work. That's the idea here. One thing I want to point out, because this was solved just like an equation. It's just, you got to make sure you're able to flip the sign, and this time you got to do a little interpreting with what the result is, because it's not one solution, it's infinitely many solutions now. One thing that I want to point out that you'll probably notice on the answer keys, notice that this is kind of messy, this graph right here. I don't like doing that, especially if I copy something, like if it's in black and white. Like I could use different colored pens and highlighters, but sometimes as soon as I like scan or copy something, it's all in black and white. And it kind of writes over numbers a bit. So it's kind of messy to see. What I like to do with number lines, let me try to remake this really quick. What I like to do with a number line is I like to keep the line itself free of writing. So let's say this was my number line. What I'll do, instead of drawing on the number line itself, what I do is I draw above the number line. Let me try to draw this a little neater. Close enough. I'll draw above the number line. And this, just for some reason, keeps it a little more visually neat, okay? And I'll put a parenthesis right there. This is just a little easier for me to see. You'll notice I do this on answer keys, so just heads up with that. That's just all that I'm doing. If you like, go ahead and draw on the number line itself. But for my work and what I do in class, I like to just draw it above the number line, just to keep it a little neater, okay? What I'd like us to do right now, I want you to pause the video and take a couple minutes to solve each of these problems. Remember, the goal is to isolate the x variable. You want to solve for x. You want to know what are all the solutions x could be for these inequalities. So use your properties of inequality, add things to both sides, subtract things, multiply, divide, and just be careful about flipping the sign when you need to. But try to get x to one side and see what your result will be. All right, well, hopefully you were able to get some work done on these problems and they weren't too foreign to you. You'll notice that the first thing I did was I decided to go ahead and clear the fraction because we can't access this x without getting rid of the negative 3 first. So I multiplied both sides by negative 3. In doing so, I had to flip the sign. Make sure that you did that. Make sure you're comfortable. Anytime you multiply or divide by a negative, you flip the sign. Not if you subtract a number. If you add or subtract a number, you always leave the inequality sign. It's only if you multiply or divide by a negative that you flip. So we had to flip here, and then we just solved like normal. I isolated x to one side, everything with x to 1, and everything without x to the other side, and solved to get 2 is less than or equal to x. I did the same thing in the previous problem as I did for the next one by multiplying both sides by negative 3 to clear the fraction. In doing so, it not only cleared the fraction, but it had to flip the sign. After it flipped the sign, I go ahead and I just combine the like terms, put everything with x to one side, everything without x to the other side, and I get 4 is less than x. So here are the two solutions. We want to write these solutions in interval notation. And sometimes drawing a number line will help us out with this. So what I'd like you to do is pause the video, take a minute for yourself, and try to draw the number line that's being represented for each of these problems, each of these inequalities. So I'll draw two little number lines right here to get us started. For me, I like to put where 0 is and where the quantity I'm working with is. For this example, it's 2. For this example, it's 4. So let's say 4's over here, and let's say 0's over here. I also like to label the infinities: positive infinity, negative infinity. Okay? Now that we have these graphed out, now that we have these graphs set up, let's go ahead and actually try to graph what these inequalities represent. So pause the video, take a couple minutes, and we'll come back in to check your work. All right, well, hopefully you had some time to work through this problem. One of the things that I want to point out here is, well, we have what our graphs represent. So I graphed the inequalities. You can see in both of these, I shaded everything to the left of the number that we were working with. So I said everything greater than 2 and everything greater than 4. I also included 2 in this example, because if you plug 2 in, you get 2 is less than or equal to 2. Well, that's true because they're equal to each other. Now for 4 here, I did not include it, because if we plug it in, 4 is less than 4. Well, that's not true. They're equal to each other. So that's why I put a parenthesis on it. So again, difference between bracket and parenthesis. Parenthesis is like an open circle. Bracket is like a shaded in closed circle. Now, let's talk about how we decided to graph everything greater than. Here's a little tip for when working with inequalities, okay? It's sometimes difficult to interpret 2 is less than or equal to x. It's difficult to interpret because we read equations and inequalities like we read sentences in English, left to right. It's difficult to interpret an inequality when the variable is on the right-hand side. What I will tend to do is reverse that, okay? I will say instead of 2 is less than or equal to x, I'll flip it and say x is greater than or equal to 2. All I did was take the mirror image of what we originally had. I still know which value was bigger, okay? That's where the sign is opening up to. That means that value is bigger. So here again, it was opening towards the x. So x is the bigger quantity than 2. Now the same thing I'm going to do right here. X is greater than 4. Again, the symbol was opening up towards the x, meaning that the x is the larger quantity. So we have x still being the larger quantity here. It's greater than 4. Now, if we wrote this in interval notation, we would say, okay, we need a low bound and we need a high bound. Well, here, of all the numbers that are solutions, The lowest they go down to is 2. So I'm going to put a 2 right here, and I'm going to put a comma. The highest they go to is infinity. So I'll say from 2 to infinity. I won't include infinity, because we never do. But 2 here, I did say before to include it, because it is a solution. So I'm going to put a bracket on 2. Now for this example, I, again, need a low bound and a high bound. We can see that the lowest these solutions go down to is 4. The highest they go off to is infinity. We never include infinity, so I'm going to put a parenthesis on that. But in this time, I said before, don't include 4 because it's not a solution. So I'm going to put a parenthesis around 4, meaning you can pick everything in between 4 and infinity, just don't pick 4. Here, for 2 to infinity, I'm saying you can literally pick any number you want between 2 and infinity. And by the way, you can also pick 2. It's one of the solutions. So these two intervals are going to be our solutions. They mean the same thing as when we wrote it as an inequality and when we wrote it in interval notation. It's just interval notation sometimes tells us a little bit more information. Hopefully this is making sense to you. What I'd like us to do right now is go ahead and try a little more complicated problems. What I'd like us to do right now is to talk about the idea of compound inequalities. Compound inequalities are collections of inequalities. So we can say a compound inequality is when multiple inequalities I'm going to say affect, and in parentheses I'm going to say constrain the variable x. Okay, so compound inequalities are when multiple inequalities affect the variable x. You have applied, instead of just one inequality, right? Some expression is greater than something is less than something, whatever. You've now applied multiple inequalities. And not just affecting the variable, but constraining the variable. This is a term we use to say you have now restricted what x could be. By adding more inequalities, you keep restricting the possibilities of what x could be for a solution. Let's see what we mean here. Take a look at this example. We have -2 is less than or equal to 3x plus 1, and we also have 3x plus 1 is less than 5. We now have two inequalities to work with. We need to find x values that produce something greater than or equal to -2, as well as something less than 5. So what we're doing is we're constraining all of the possibilities of x. There's a couple ways of going about solving these problems. Technique number 1 is to split up the compound into multiple inequalities. By that I mean what we just said before. I'm going to say this is technique 1. We just said before that -2 is less than or equal to 3x plus 1. And we also have 3x plus 1 is less than 5. What we just did here is we split the compound inequality into two separate inequalities. And what we're going to do is solve them separately. So let's solve these separately. Let's subtract 1 from both sides. We get negative 3 is less than or equal to 3x. I'm going to divide both sides by 3, and we get x greater than or equal to negative 1. I didn't flip the sign here, okay? Make sure you recognize that we don't need to flip the sign because we divided by a positive number. Additionally, over here, let's subtract 1, just like we did before. We get 3x is less than 4. If we divide by 3, we get x is less than 4/3. So we are saying that the solutions for this compound, you have to pick numbers greater than negative 1, I should say greater than or equal to negative 1, but also less than 4/3. 4/3 is 1 1/3. So you're really restricted down at what you could pick. That's technique 1. Technique 2, we're going to say isolate x to be in the middle of the compound. So you have the compound inequality here. Now, the other technique is to just get x by itself in the middle, and we'll see what we end up with. So here is technique 2. Let's see, negative 2 is less than or equal to 3x plus 1, which is less than 5. What I'm going to do is I'm going to subtract 1, but this time I'm going to do it to all sides. Because if I subtract it from one of the sides, I have to subtract it from all of the sides. Negative 3 is less than or equal to 3x, which is less than 4. And if I divide everything by 3, we end up with, let me get a little more space here. We will end up with negative 1 is less than or equal to x, which is less than 4/3. Again, the same thing right here. It's just we can see it all written together. We need to pick values for x that are between negative 1 and 4/3. We could pick negative 1 because it's included here, but we can't pick 4/3 because it's not included there. So it's really easy to write this solution. I'll write it in red because we already have the bounds. Everything between negative 1 and 4/3. Let's write that a little nicer. There we go. We know not to include 4/3 because it's just a less than sign here. And we know to include negative 1 because it's less than or equal to. So I'll put a bracket on negative 1 and a parenthesis on 4/3. There we go. That's it. That's our solution. Of these two techniques, pick which one you like. Some people really like technique 2 because they like how it gives out the answer. Other people are like, no, technique 1. It's straightforward and makes sense. So your choice. What I'd like us to do right now is to pause the video and to take a couple minutes to go ahead and practice these techniques, using them to go ahead and solve these inequalities. Make sure to write your solution in interval notation. If you have any questions, we'll hang back for a minute and we'll go ahead and take a look at the work and see what we produce. All right, well, hopefully this problem was making sense to you. I used technique 2 for this situation. What I first did was, if I got to get this variable y to be by itself, well, then I have to get rid of the denominator 6. So I have to clear the fraction. So I multiplied all 3 sides by 6. I got negative 30 for the one side, negative 48 for the other, and in the middle I was just left with negative y plus 3. I added 3 this time, again, to all 3 sides, so I ended up with negative y, and that was less than or equal to negative 33, but still greater than or equal to negative 51. Again, this was only what negative y was related to, so to solve for positive y, I divided both sides by negative 1, and I flipped the signs. That's important. We have to flip the signs here. So it's everything between 33 and 51. So if I was to write this in interval notation, everything between 33, comma, 51. Now in this case, do we include the endpoints? Should we include 33 or 51? And in this case, yes, we should. Bracket on each. Because 33 is greater than or equal to 33, but less than or equal to 51. And if you plug 51 in, it's less than or equal to 51, but still greater than 33. So that's the idea here. Let's go ahead and see if that makes sense for the second problem. Let's see if we can use a similar technique for this one. Well, it looks like actually x is already by itself, so I don't need to do anything. We have numbers for x that are between -1 and 3. So those are our bounds, -1, comma 3. 3 being greater than 3, well, that's not true. So we're going to put a parenthesis here. What about -1? Is -1 greater than -1? No. So we'll put a parenthesis on that. So we're saying any number between -1 and 3 will satisfy this inequality. Well, hopefully you're recognizing, wait a minute, that doesn't sound exactly right, does it? Pick a value in here. Pick something in here. Something in this set between -1 and 3. Pick something like +1. And let's test it out. So test x equaling +1. We end up with -1 is greater than 1, which is greater than 3. Is that true? Is -1 greater than 1? No, that's not true. And is 1 greater than 3? No, it's not. So what's the issue here? We were trying to find numbers that are greater than 3, but also greater than, or I'm sorry, less than -1. Well, if we graph that, let's put a little number line down, and let's try to shade in what's going on here. -1, 0, 3. In the blue, this is everything greater than 3. And then in the, I'll do in the green this time, this is everything less than -1. Here we can see, are there any numbers that satisfy both of the inequalities? Are there any numbers greater than 3 that are also less than -1? Well, no. There are no such numbers that do this, okay? See, none of their graphs have anything in common. None of their solution sets have anything in common. So this, we could say, would be no solution. There is no solution to this because there's no overlap here. There's nothing in common between these sets. There's nothing that will work for both inequalities. That's the idea of this section, going through and working with inequalities and being comfortable applying these properties to manipulate them. If you have any questions or comments or want to let me know what you thought about the video, please feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video, if you have any questions, and until next time, take care.